Greetings, I am Boris Resnick, and today I present you a method to detect vague vortices using convolutional neural networks. A hazard of the vague vortices. A heavy aircraft flying on a low speed generates a trailing air turbulence called vague vortices. These vortices can present a considerable danger for a following aircraft, especially of a lighter category. To address this issue, air traffic control apply increased separation between the aircraft. Excessive separation distances can lead to inefficiency in airspace usage, especially in terminal airspace of major hub of highly mixed traffic. Stronger concerns were raised with the introduction of Airbus 380 Super Heavy aircraft. Direct vortex measurements and detection can help to analyze potential threats and increase efficiency. Scanning Doppler lidars can be used to direct vortex measurement at low altitudes. To perform such a measurement, we deploy a lidar under special geometry constraints. Lidar is positioned sideways over runway in the immediate vicinity and scans vertically in a plane orthogonal to a runway extended centerline. LiDAR measurements are valid within specific distance limits, generally from 100 to 600 meters. Elevation angles are set to capture the whole zone of potential vague vortex existence, generally from 0 to 30 degrees. LiDAR digital output consists of a set of scans. Each scan corresponds to a single path of LiDAR reciprocating motion. At each elevation angle, LiDAR senses a projection of a wind speed v to a scan line at a set of distances. Single LiDAR scan representation in polar coordinates is shown on the slide. Number of measurements in a single scan n equals k by m is determined by scans angular, a half of degree, and range, 3-meter resolution. Existing ad hoc algorithms are based on direct analysis of a wind speed value behavior. Specifically, high gradient values of v together with a change of sign or direction along the adjacent array constitute the presence of a vortex. This approach has both advantages and disadvantages. As a main advantage, these algorithms can be used to derive quantitative characteristics of a vortex coordinates and circulation strength. However, these methods work under two assumptions. Firstly, a vortex has a delineated circular structure, and secondly, radial wind speed distribution has a particular shape. And the last assumption is not precisely correct near a ground plane when its interference with a vortex creates secondary vortex structures. Hence, overall vortex geometry deviates for a circular shape. To address this problem, we follow an alternative approach which is less sensitive to a priori vortex structure, namely neural network approach. In this study, we use well-known object detection process applied to bitmap representation of the scans. Vortex as an image. To create a data set for a convolutional neural network, we represent vortices as a tensor I of three component red, green, blue color vectors. A deterministic transform C is used to calculate a color from a wind speed v. A lower bottom of this rendering shows a typical vortex structure. We use a model to generate a comprehensive set of modeled LiDAR measurements for a varying set of parameters. A render shows a couple of generated vortices. The left one and the right one. In order to obtain a training set that adequately reflects both ambient air turbulence and vortex images, we apply a blending procedure. For each modeled vortex pair, we randomly select an image labeled as a clear background. Labeling of these background images was done manually. For this study, we use a well-known neural network architecture Faster RCNN method is used with Inception version 2 architecture pre-trained on the COCO dataset. Implementation is based on TensorFlow library with GPU support. We use a single detection class, a Vortex. Number of training steps 200,000. Training set comprises 80% of the sample, while testing set comprises 20% of the samples. Validation uses direct Vortex measurement. Detection results. This rendering represents a sample detection of a couple of real wake vortices with a certainty of 92 and 99% correspondingly. So this concludes my presentation, and thank you very much for your attention.